Okay, now that we've studied pressure and density, we can move on to study fluids. So our first lesson in fluids is hydrostatic pressure. So first, let's define a fluid. A fluid is any substance that has no fixed shape. Generally, we think of this as either liquids or gases, but there can be some other more non-conventional fluids. Um, the big idea with a fluid is that if you apply a force, so if your thumb pushes here on this water balloon or something, that force is distributed equally all around the water balloon. So pressures in general are transmitted to other points in the fluid. So the pressure is distributed throughout a fluid. If it was a solid, then obviously pushing on one end wouldn't necessarily transfer the pressure to some other place in the solid. But that is true of a liquid or a gas. So Pascal's principle, which is basically this idea that pressures are transmitted everywhere in a fluid, is the basis of what we call hydraulics, which use fluids to distribute forces. So in hydraulics, if you apply a force over here, that force divided by the area which it is applied creates a pressure in the fluid here. And because it's a fluid, the molecules can move and that pressure is transmitted all the way over to the other side. And then if you have a large area here, that can produce a very large force because the pressures at A1 and A2 are the same. So if you have a bigger area, you'll have a bigger force. Now, basically, it gives you a mechanical advantage. If you move the F1 a distance of 1 meter, F2 might only move 0.1 meters, but it'll have a much larger force. The work done is the same, of course, but you can use fluid to transmit forces through fluids in the field of hydraulics. So what we're going to look at is fluid pressure. So in a fluid, the pressure acts in all directions. This is not true if you were standing next to a pillar of concrete. The concrete would exert enormous force downwards, but if you were standing next to it, it wouldn't exert a force on you. But the atmosphere is a fluid, and so when it pushes down on the earth, it also acts in every other direction. So if this is you over here, the atmosphere is actually pushing on you in all directions. So pressure is transmitted everywhere in a fluid, and it acts in every direction in the fluid. So that's an important idea. It's part of what's called Pascal's principle. So what we want to do is figure out what is the pressure on the bottom of the swimming pool here. So imagine we have a rectangular swimming pool, and we're going to calculate the pressure on the bottom, and we're going to fill it with water. So to start, we know the pressure equals the force over the area. So we need to find the force of gravity pulling on this big cube of water and divide it by the area, the blue region here, over which that force is spread. Now, we know that force equals m times g, so if we could find the mass of the water and multiply by g, we would have the force. And we also know that the area of the bottom of the pool is the length times the width, L times W. So if I substitute those in, I can calculate the pressure as mg over L times W. Now, it's also possible to use the density of the water. The mass of the water will be the density times its volume. So I'm going to substitute that in here for the mass. So instead of mass, I'll have density times volume times g over L times W. And then lastly, we know the volume of this pool, the amount of water it holds, is given by the length times the width times the height. And so if I substitute that in for V, I get this expression for the pressure on the bottom of the pool. And the interesting thing to note here is that the length and the width appear in both the numerator and denominator. So those cancel and just leave us with the pressure on the bottom of the pool is rho, the density of the fluid that's in the pool, times g, the gravitational constant, times h, which is the depth of the pool. So this is the formula we call the hydrostatic pressure. So the pressure on the bottom of the pool doesn't depend on its length or its width. If you had a pool that was smaller or bigger, how much pressure you have on the bottom only depends on how deep the pool is, not its size, not how long or wide it is. So it's a little harder to show using a simple calculation. You need calculus to do it. But you could also show that if you look at the pressure at the bottom of all of these funny looking shapes, the pressure is also the same at the bottom. The pressure doesn't depend on the geometry. It doesn't depend on the shape of the container. The pressure right here is the same as the pressure right there, which is the same as the pressure right here below the orange fish. And you can imagine if the pressure right here was greater than the pressure over here, water would move and rearrange itself. But water always goes at the same height, and so that's sort of an intuitive argument for why the pressure is the same. but regardless of whether we can prove it in calculus or not, the fact is that the pressure in a fluid only depends on the depth of the container. It doesn't depend on the shape. Okay, so this is the formula that you're going to need to put in your toolbox. This is what's called hydrostatic pressure. If you want to find the pressure in a fluid, the pressure that's due to the fluid, you need rho, the density of the fluid, g, the gravitational constant, and h, which in this case is the depth of the fluid, and that's going to be in meters. Your density is going to be in kilograms per meter cubed. The gravitational constant, of course, is meters per second squared, and your pressure will then be in pascals. Here's two examples. You may have noticed that when dams are built, the bottom is thicker than the top, and that's because of what we call hydrostatic pressure. The pressure on the dam wall gets greater and greater the deeper and deeper you are. So it doesn't matter how big the water reservoir is, the pressure on the wall depends on the depth. And so the deeper it is, the thicker you need the wall. So dam walls are shaped in a way that the bottom is thicker than the top. Another example, a fluid or corn acts like a fluid sometimes. And so if you have corn or grain, the pressure gets greater and greater the deeper and deeper you go. And so you can notice that the reinforcing bands on silos actually get closer and closer together to withstand the greater pressure of the fluid at the bottom than at the top. So those are two examples of this hydrostatic pressure principle. Okay, so let's just solve two example problems to make sure we understand this. First of all, at the high school diving pool, or the diving side of the pool, the depth is about 13 feet, and we want to find the pressure at the bottom of this pool. And we're going to find our answer in pascals and then convert it to PSIs and in atmospheres. So the first thing we need to do is write down what we know. We know the density of water, so let's assume there's water in the pool, is 1,000. And we know the depth of the pool is about 13 feet, which is about 4.0 meters to two significant figures. The hydrostatic pressure is rho times g times h. We substitute in our numbers, and we come up with about 39,000 pascals, or 39 kilopascals. We don't really have a way to know what that means. We aren't used to pascals or kilopascals, so it's helpful to convert that to units we are more familiar with. So if I take my 39,000 pascals, multiply by the conversion, there's 1 atmosphere and 101,000 pascals, and I get 0.39 atmospheres. So basically, when you're at the bottom of the diving pool, and you feel that extra pressure on your ears probably when you dive to the bottom of a pool, the pressure down there is about 40% of the pressure of the atmosphere. So our atmosphere actually pushes really hard on us, the air above us. And so at the bottom of 13 feet of water, the force you feel due to the water is about 0.39 atmospheres. If you're used to PSIs, pounds per square inch, you can also convert atmospheres to pounds per square inch. There's 14.7 psi in 1 atmosphere. So that's about 5.7 pounds per square inch. So every square inch of your body is feeling a force of 5.7 pounds due to the water pushing out in all directions. A quick note, we call this 39 kilopascals the gauge pressure. It's the pressure due to the water. If you're doing a chemistry experiment down there, though, you would need the absolute pressure. And the absolute pressure down here would be the pressure at the top of the pool, which is the atmosphere, plus the pressure that's due to the water, the extra pressure. So in that case, the absolute pressure would be 1.39 atmospheres. There's 1 atmosphere of pressure due to our atmosphere, plus an extra 0.39 atmospheres due to the water. So the absolute pressure at the bottom is 1.39. Okay, a second example involves a submarine which experienced an explosion and was disabled, and it sunk to the bottom of the Barents Sea. And the Barents Sea isn't very deep. So here's a picture of the submarine, and it's not even as deep as it is long. And you can see the Eiffel Tower right here next to it for comparison. So it's not really that deep. It was 107 meters of water. But the sailors who survived the accident were trapped in there. They were alive, but they couldn't open the hatch to escape. And that's because of the hydrostatic pressure of the water. So we're going to calculate the pressure down here. So here's the question we want to solve. At a depth of 107 meters, what is the force that would be exerted on an escape hatch if it had a radius of 12 inches? So we've got an escape hatch. It's 12 inches in radius, and the seawater is pushing in on it. And what force would you need to open that sea hatch? Because on submarines, obviously, the doors open outwards if you're 107 meters deep in the water. So here's our diagram. What we know is the density, because it's seawater, the density is slightly greater than fresh water. The depth in the water is 107 meters, and the radius of our little circle here is 0.305 meters. So our plan is to find the force that's required. So the pressure is the force over the area. So the force is the pressure times the area, and the way we're going to find the pressure is we're going to use our hydrostatic equation to find the pressure down at that depth. So the pressure equals rho times g times h. We plug in that for the pressure, rho gh, and for the area, we take pi r squared because it's a circle. Plug in all of our numbers, which are listed over in our variable list, and it turns out to be about 314,000 newtons, or 70,000 pounds. So the reason the sailors couldn't open the escape hatch is because there was 70,000 pounds of force exerted on that circular hatch, keeping it closed, and there's no way humans could exert that much force to open it. So that's how we can use hydrostatic pressure. Anytime you're in a fluid, you're submerged in a fluid, there's a pressure on you, and the pressure that's on you depends on the depth of the fluid, the density of the fluid, and the gravitational constant. It does not depend on the shape of the container. Okay, you've got some problems to solve there.